Assalamu alaikum. My name is Hussain Ali Akbar and my topic of EM case study is electric machines used in a diesel electric locomotive. Rolling stocks of railways can be broadly divided into powered and unpowered groups, where powered rolling stocks give driving power to the train and unpowered rolling stocks get hauled by them. Powered rolling stocks can be further classified into autonomous and non-autonomous categories, where non-autonomous, like electric trains, get their power supply from external sources, and autonomous vehicles have power plants mounted inside them, allowing significant reduction of environmental impacts on operation and improved use of energy. Although large onboard spaces are required and weights are increased, traction energy consumption decreases 15 to 35% in autonomous locomotive applications. Power peaks at acceleration are minimized and losses in catenary lines are excluded. Diesel electric locomotives are one example of these vehicles and are currently serving on more than 1 million kilometers of railways track length. This presentation first briefly discusses the general electrical requirements of a locomotive and then explains all the electric machines employed in a diesel electric locomotive with a comparison of DC and AC technologies. Firstly, to counter no torque condition by diesel engine at standstill, the engine must be kept running with clutches and torque converting transmission mechanisms to ensure proper amount of tractive force in different states of operation. Traction force requirement is inversely proportional to the speed of operation, and the resultant performance curve is named hyperbole and is shown in the first graph of the slide. Any point taken on the curve will yield the same horsepower, that is, the capacity of the diesel engine remains constant on the entire curve. This permits this permits optimal control or fullest use of diesel engine power in the entire speed range. Consequently, load characteristic curve of traction generator with constant electric power must also be hyperbolic in shape. We must remember that changing gear ratio of installed traction motors alter the limits of the speed traction force and can effectively move the range of performance at constant horsepower. The actual horsepower demand is very small at the start and gradually increases to its highest limit with increase in speed. And to meet this need, speed of the diesel engine is also gradually increased to full speed as the locomotive speeds up. Lastly, the size of the generator and the motors installed in the system dictate the proportion of speed range over which the employed transmission equipment is rated. Keeping in mind the list of general characteristics of locomotive and design requirements, the electric machines in a diesel electric locomotive can be broadly divided into engine, generator set, and traction motors based on the purpose they serve. Every diesel electric locomotive resides a constant speed, constant power engine to operate a shaft that drives all other components vital to power the locomotive. As a compromise between the demand of high speed, maximum reliability, and low maintenance, a medium speed engine is typically installed in most locomotives. British built traction applications mostly use 4 cycle engines, though 2 cycle types are also employed in locomotives. Supercharging permits increase in engine horsepower and is very commonly relied on in high speed but lightweight locomotives. Higher units up to 1000 HP use in line engines with 6 to 8 cylinders. Even higher units 1000 HP to 2000 HP most commonly use engines in V arrangements. The generators in locomotive are typically coupled with the engine. They are built specifically according to the traction standards and serve as a very flexible power link between the engine and the motors for variable voltage supply. The most employed generator field system is shown in the figure on the slide, where A is the separately excited field for power regulation and B is the self-excited shunt field for reduction of range required on external regulators. Here A and B are additively working together, and to complete the design as a short rated series field is also included that guarantees enough torque generation to start the diesel engine. Parameters on uh, all the parameters given on this slide are considered for choice of right traction motors for locomotives under consideration. 40% of the locomotives manufacturing market currently manufactures electric tractions with DC motors. Material requirements, mainly semiconductor requirements for construction, are relatively simpler. Speed control is possible using different connection variants to power supply and their windings, and they allow easy transition between motor and generator modes for dynamic braking operations. However, control stand maximizes addition at full power, hence it is very harsh for DC motors when operating at high load values and low speeds because it necessitates high armature current. Resulting power losses in field and armature windings generate high heat, causing insulation breakdown, motor degeneration, and eventual failures. DC traction motors are more expensive and complex compared to AC traction motors, and power more than 1500 kilowatts cannot be implemented using the existing models of DC traction motors. Moreover, brush gear and commutators require dry, cool, and clean environments to maintain their condition. Squirrel cage AC induction motors are also used as traction motors and are most prevalent in the current time, dominating 60% of the traction manufacturing market, mainly because of their simplicity, durability, and reliability. Since the induction motor has no since the connection between the stator and the rotor, there are no brushes and commutator, and they allow implementation of braking efforts with very large brake forces, recovering more energy when used in regenerative braking mode and eliminating the need and consequent cost of the braking mechanisms. Locomotives are named either AC or DC locomotives depending on only the type of electricity used by their traction motors without any indication of the supply type employed. We now refer to a research that uses AAR train energy model software to evaluate AC locomotive traction performance against DC traction system, considering a 3000 kilowatt AN class DC locomotive and a 400 HP AC locomotive for simulation and data generation from a TEM software. Graph 1 from their results the loading hauling ability of the two types of locomotives under consideration, which is dependent on the maximum power generated by traction motors and addition coefficient between the wheels and the traction of the respective locomotive. Coefficient of AC locomotives is 0.39, higher than 0.27 addition coefficient of DC locomotives. Resultantly, they have improved hauling ability at steep ruling rates. Also, the curve of AC locomotives is flatter with respect to slope and is lower in magnitude, which represents shorter travel time for a given amount of load and smaller increase in time with increasing load within a given range of trailing load. Fuel consumption graph plotted against trailing load in the given figure represents fuel efficiencies of both types of locomotives. Clearly, AC locomotives are more fuel efficient, consuming 5.5%, 200 liters less fuel than their DC counterparts in the same travel at a given load. AC locomotive curve has a relatively flatter gradient representing lesser marginal cost of fuel for every addition in load. This figure compares fuel consumption of two locomotives within specified times. AC locomotive again proves to be more efficient. They clearly accelerate faster to maximum speed owing to the increased tractive effort from the rail power operation speeds and longer coating. They accelerate faster to the maximum speed owing to the increased tractive force from the rail, which permits lower operation speeds. This provides decrease in fuel consumption for AC locomotives. All the auxiliary loads are provided. Power by auxiliary generator. This power system is a converter charging the system service battery and generating 400-volt AC 50 Hz grid on board. The voltage is maintained constant at all operation speeds, and AC output frequency is allowed variation of 5 to 10% and can be between 50 to 60 Hz, although the DC output depends on the service battery. These power systems are designed with galvanic insulation, and electric isolation can be guaranteed with proper transformer topologies for low frequency applications and advanced converter topologies for high frequency applications. These are the references from which all the content has been taken. Lastly, I'll comment that technological advancements with time are common and has led to advancements from steam to diesel electric to electric trains and locomotives. Targets of all advancements in this domain are higher power, higher speed, higher higher traction, higher energy efficiency, and better operational performance. This paper and this presentation only focuses on one of the several types of locomotives that are used around the world to allow deeper understanding of electric machines employed in locomotives with appropriate analysis. Thank you for listening.